actually several different structures of the snake venom, and its unique factor is that it is able to basically cut apart your cell membrane. So we've found that, like, in addition to damaging the cells, it's also able to basically help with signaling and telling the parts of your body how to function. And the specific isoform, of which there are 11, I'm looking at is called group 10. And it is highly linked to releasing this molecule that's linked to inflammation. But what does inflammation have to do with cancer and the immune system? So I'm trying to answer here. I'll answer that very soon, but first I have to show you what it looks like. So since this past year, I've tried to figure out how to recreate the structure because I'm very interested in it. This is Phospholipase A2 group 10. It's got like this kind of handshake, and what it's basically doing is existing on the outside of your cell. It'll sit on your cell membrane. Do you guys remember the phospholipid bilayer? Yeah. It'll sit right outside of your phospholipid bilayer, grab one of them just like this, and then rip out one of the fatty acids. And this one is the one that's linked to inflammation. But basically, my honors thesis was on bridging that art and science project because I just find it very important to communicate that. And if we want, we can pass this around. The only thing is that it's made of bobby pins. But if you want to pass around and try, I am more than willing. So you guys can pass this around while I continue to present the topic. All right, this is supposed to be a magnet. There you go. Okay. Thank you guys for But yes, I was able to find the crystal structure and I recreated it from a previous study. But after using that and having a magnet removable structure, I basically explained that the specific phospholipid that it's very good at cleaving is very commonly found on the outside of your cell membrane. It's known as phosphatidylcholine. And I basically explained that it tends to release arachidonic acid, which is that curlier polyunsaturated fatty acid. It lasts for a very short time in the body, and you know when you take ibuprofen or Advil to reduce your pain, that's supposed to block the conversion of arachidonic acid into other signaling molecules. So it's really interesting to think that the enzyme that we're looking at here is just one step above that. And how does this matter in the context of cancer? Okay, we're getting to this now. Immunotherapy. Who knows what immunotherapy is? Yeah, immunotherapy is basically having your body fights cancer all the time, and your immune system is very linked to that effectiveness. But your main soldiers of your immune system are known as T cells, and they have to kind of grapple like Spider-Man towards the cancer. So they're doing what's called chemotaxis, and they're basically randomly sniffing chemicals towards them. Immunotherapy has great success in certain types of cancers, but in others, it really doesn't, and we're really trying to work on that and expand its accessibility. But to think that we have an additional therapeutic strategy amongst surgery and radiotherapy and chemotherapy is very important. So immunotherapy resistance comes in terms of hot and cold tumors. There's no official clinical definition for this yet, and we're still trying to figure this all out. But so far, we've found that the molecular basis is how well the T cells are able to respond and act on cancer. So what is the molecular basis for hot tumors? The T cell response, but what is the cold tumor response? PLA2 group 10 may be a T cell excluder, and its effect of creating all of those little lipid trimmings may be responsible for creating this lipid environment that prevents chemotaxis, as we saw in this in vitro data. They had these chambers where they have tumor cells on the bottom chamber, and the chemoattractants placed with PLA2 group 10 acting. And they found that the T cells were not able to migrate as well towards the cancer. And they even removed the enzyme itself and had its downstream products present, and the same effect happened. But once you blocked the enzyme's activity with a pan inhibitor, which is across all the different shapes, they found that T cell migration was rescued. So there's a lot to apply here for the dynamic tumor microenvironment, especially non-small cell lung cancer. To think that we can use this enzyme and turn cold centers is why this matters, but this highlights the importance of precision medicine and the idea that everyone's cancer case is different. And there's just a lot to be seen for finding the complexities of the molecular ways that we interact in our body and what the T cells do. So, thank you. Do you guys have any questions? Because I've got a poster here as well.